Okay, so this is the last lecture video of the semester. We are going to be reviewing for the last exam covering chapters 42, 43, and 44. So let's get started with chapter 42, which is nuclear energy and radiation. So in nuclear reactions, nucleon number, and remember that's the total number of protons and neutrons, and charge must be conserved. In radioactive decay, that's not necessarily the case, but nucleon number and charge must be conserved in nuclear reactions, and the mass contained within the nuclei might be different after the reaction, which means energy has been either gained or released. So for energy to be gained, that means the particles involved had to be moving. So there had to be some sort of kinetic energy supplied to the nuclear reaction in order for the reaction to take place. Uh, if they're released, if the energy is released, then it's not necessarily you don't necessarily need an input of energy. So the reaction energy of the Q is the net amount of energy released. If the reaction has the form A plus X becomes Y plus B, then Q is equal to the initial mass, the total initial mass minus the total final mass multiplied by C squared. Now, often you see the mass expressed in atomic mass units, so you'll need the conversion factor between, going from mass units to mega electron volts to figure out the Q term in this. An exothermic means there's a net release of energy. Endothermic means there's a net input of energy, or Q is less than 0. The cross section of a particular collision is a measure of the probability of it happening. And it's measured, typically expressed in units of area or in square meters. So the bigger the cross section, basically the bigger the target. And the bigger the target, the more likely it is for a particle to hit it, for a collision to take place. So nuclear fission is the splitting of a heavy nucleus into lighter nuclei. And the most obvious example involves uranium-235. So you have an atom of uranium-235, a neutron hits it, and so the uranium absorbs that neutron and becomes uranium-236. But uranium-236 is extremely unstable. It lasts, as a lifetime of 10 to the negative 12 seconds, so a very small lifetime. And before it will decay into two lighter atoms, plus energy, plus more neutrons. And so what happens is the released neutrons then go flying around and hit more uranium atoms, causing more fission, which releases more neutrons that hit more uranium atoms and so on. And so that's called a chain reaction. But the basic reaction is described as a neutron plus uranium-235 becomes barium-141 plus krypton-92 plus 3 neutrons. And again, the 3 neutrons are, are moving away with a sizable amount of kinetic energy, which makes it easy for them, if you're talking about a sizable enough sample of uranium-235, it makes it easy for them to find more uranium-235 atoms and cause more fission. And so that's a chain reaction. And in a nuclear power plant, that chain reaction is controlled. So there's a limit to how rapidly that reaction can take place. In an atomic bomb, that's a different story. The whole point is that the reaction is completely uncontrolled. And so all that energy gets released at once. Typically, the amount of energy released by the fission of a single heavy radioactive atom is about 100 million times the energy released in the combustion of one molecule of octane that can be used in gasoline engines. So the key to nuclear power is the enrichment of the atom. You want as much of the uranium sample to be uranium 235, or you want to optimize the amount of uranium 235 in your sample. So in nature, uranium 235 is about 0.7% of the total uranium. So most uranium is a different isotope, but uranium 235 is the best for nuclear fission. For a power plant, the uranium sample is enriched to 4% um, uranium 235. And for weapons grade, it goes up to about 90%. So it's not that hard to tell what, if you have a sample of uranium, it's not that hard to tell what it's going to be used for. So the most common uranium isotope is uranium 238, but uranium 238 does not split very easily, whereas uranium 235 does. The major cost of nuclear power plants comes from the construction. It's actually relatively cheap to maintain once you've got it up and going, but the cost of setting up the plant and establishing quality control and safety, and having the very complex process run smoothly, there's a very high upfront cost, which makes it kind of prohibitive compared to other energy sources that are out there. Nuclear power plants, I think the first nuclear power plant was built in the 1950s. Nuclear power reached 20% of US electricity production in the United States in the early 1970s, but it's never gone above that. And safety concerns stemming from a couple of incidents, 3 Mile Island here in Pennsylvania in 1979, the much greater disaster at Chernobyl in 1986, 24,000 cancers, large stretches of land rendered unusable. What happened in 3 Mile Island was basically nothing in comparison. And also Fukushima in 2011 in Japan. And but perhaps most significantly is that natural gas and renewables have dropped in price, where the cost of nuclear power has gone upwards. The best uranium ore is running out. So that would cause an further increase of the price, but it's still fairly small relative to the construction of the plant. But Fukushima happened in Japan on March 11th, 2011, and it did cause some damage, and there is radioactive water in the Pacific Ocean as a result of Fukushima. But to this point, the death toll due directly to the radiation leakage is tiny compared to what happened with the earthquake and the resulting tsunami that caused the meltdown, along with many other things. One issue with nuclear power is nuclear waste, that once you've used the fuel, it's still radioactive. What do you do with it? And part of the problem is finding a site that people near the site will be okay with. And it's not very, it's an ongoing issue that's never been adequately resolved. So that brings us to nuclear fusion. Nuclear fusion is when two light atoms fuse to form a heavier atom. And the sun's energy comes from nuclear fusion. The key with fusion is that the two nuclei must have a very high kinetic energy to start with for them to overcome the repulsion, the electric repulsion due to, if it's a hydrogen atom, if you get the two hydrogen nuclei close to each other, they're going to repel each other. So you need a high kinetic energy to overcome that and make the collision happen. So you need a high temperature and a high collision rate to sustain the fusion. And that's been a major issue for practical utility scale fusion, that fusion, controlled fusion reactions haven't reached the break even point where they release more energy than is put in. But the basic reactions are the two hydrogen atoms make deuterium plus a positron plus a neutrino. And then another hydrogen atom reacts with the deuterium to make helium plus a gamma ray. So very high energy photon. So the basic reactions in the sun, for example, you have two hydrogen atoms making deuterium plus a positron plus a neutrino. Another hydrogen atom fuses with the deuterium to make a helium atom plus a gamma ray. And then two helium atoms fuse together to make hydrogen plus, or to make helium plus two more hydrogen atoms. So the net result is four hydrogen atoms become a helium 4 atom plus two positrons plus two neutrinos plus two high energy gamma rays. So there's quite a bit of energy released for the amount of mass that's put in. Fusion was considered the energy of the future in the 1950s. It still is. The practical hurdles for utility scale fusion have not been overcome. We have yet to cross the break even point in a controlled fusion reaction. But there are still some attempts to create fusion. So you have what's called a tokamak reactor, where you have magnetic confinement. So the hydrogen atoms are held in place by a very powerful magnetic field and then brought close enough together that they can fuse. And so, that's one example. And the National Ignition Facility is using lasers to supply the heat needed to start the fusion rather than a nuclear reaction. Often it takes fission to start a fission reaction to start the fusion process. And again, break even hasn't happened with any of these attempts at fusion. One practical application of fusion is beam fusion, which makes it possible to investigate the rocket drill site. So it's not breaking even, but it allows targeted energy to break rock. And you can have muon fusion with liquid hydrogen. That's been demonstrated, but it still takes more energy to create the muon than you get out of it. And that brings us to radiation and radioactivity. So charged particles can ionize the atoms or molecules of anything that they pass through. And so losing electrons can break apart molecules. When you break apart molecules in organic tissue, you're damaging the organic tissue. You're interfering with cellular processes, you're damaging DNA, you're causing health issues. So how do we quantify these health issues? So we need to quantify the dose of radiation. And so one unit that's often used is the Curie, which is 3.70 times 10 to the 10 decays per second, which corresponds to the activity. So activity goes back to chapter 41. So the activity of 1 gram of radium. And, so that's defined as the Curie. And so suppliers of radioactive material specify the activity at a specific point in time. Because if you know the material and you know its half-life, and you know what the activity was at a specific time, you define that time as t equals 0, and then you can figure out the activity right now, or when the radiation is administered, assuming it's administered for health purposes. 1 rad, another type of radiation unit, is the amount of radiation which deposits 1.00 times 10 to the negative 2 joules of energy in 1 kilogram of absorbing material. One gray, the SI unit, deposits 1 joule of energy per kilogram, and that corresponds to 100 rads. 1 rad of alpha radiation is more damaging than 1 rad of beta or gamma radiation. So for the same energy, you think kinetic energy is equal to p squared over 2m. That's the momentum then is equal to the square root of 2m times the energy. So for a same amount of energy, the more massive object has a greater momentum. And so alpha radiation, being a helium nucleus, has more momentum for the same amount of energy than a beta particle, which is an electron, or a gamma ray, which is a photon. And so that brings us to the relative biological effectiveness or quality factor, which is the amount of biological damage that a certain amount of a given radiation does compared to the same amount of energy for X or gamma rays. And so we can talk about the effective dose in REMS as being equal to the dose in rads times the quality factor, or in SI units, the effective dose in sieverts equals the dose in grays times the quality factor. The average American experiences 360 millirems per year of radiation. So that's just from, the natural background. You'll almost never be able to prevent exposure to radiation absolutely, in just a natural setting. But it also includes medical visits as well. So, it's taking into consideration that, maybe you'll get an x-ray or something like that once a year. Or, whatever the amount of x-rays a person gets on average gets factored into that. So 400 millirems per year above the natural background is considered dangerous. So these are the quality factors. So X-rays and gamma rays have a quality factor of 1 by definition. Beta particles, approximately 1. Fast protons, about 1. Slow neutrons are about 3. Faster neutrons can be up to 10. Alpha particles and heavy ions can be up to 20. So there are multiple factors that go into why certain things affect quality factors. So momentum is part of it, but it's not the full picture. So radiation is dangerous, but it can also be used for health applications. So cancer cells are especially susceptible to destruction by radiation, but you have to be careful. You want to destroy all the cancer cells while not destroying the healthy cells. And, that's been a very big challenge in cancer therapy for a very long time. So one way you try to do that is you rotate the radiation source around the area, the target area, to minimize the exposure to a particular region of healthy tissue. One thing you can do is called proton therapy, because protons deposit nearly all the energy at the end of their path. The catch with proton therapy is you need, in order to get a steady stream of protons, you need a particle accelerator happy, and there aren't that many particle accelerators around. A radioactive isotope called a tracer can be injected or ingested into the body, so it can be monitored as it travels. So this is one way to look at to look for blockages and that sort of thing. If things are running smoothly, you'll be able to see that. But if you're looking for where they're not running smoothly, you'll be able to find that using a tracer. Probably the most obvious example of using radiation for health purposes is an X-ray. Bones absorb X-rays very easily. Regular tissue like skin or muscle does not. So X-rays make it possible to examine the bone non-invasively. You don't have to cut a person open to tell whether their bones are broken, and that's there's an obvious benefit to that. Other types of radiation used for imagery, you may have had a CAT scan at some point. A CAT scan is an example of tomography where you have multiple images taken at different angles that can be processed into a three-dimensional image. And so the CAT stands for computerized axial tomography. And with emission tomography, you're using a tracer. So instead of an X-ray scan, you're using a tracer to create the three-dimensional image. Nuclear magnetic resonance is when uh, the nucleus or the energy state of the nucleus can split in two in the presence of a magnetic field. And the split is different for bonded and unbonded atoms, providing information on molecular structure. So you can find information out using nuclear magnetic resonance. And with an MRI, you can alter the frequency of the radiation, meaning the wavelength of the light, basically, as a function of location that can tell you where the photon has been absorbed. It's quite a bit less invasive than X-rays or gamma rays. So that's all for chapter 42. Let's now move on to chapter 43. So we talked about the elementary particles. And so the most basic way that we've created collisions, high energy collisions involving basic atomic or subatomic particles is with what's called a cyclotron. So basically a uniform magnetic field keeps particles moving in circular paths. And you set up your cyclotron, you want to make the momentum as large as possible, because the greater the momentum, the lower the wavelength and the greater resolution with which you can observe what goes on at the atomic or subatomic level. So in cyclotrons, there's typically a narrow gap between two D-shaped cavities that are called the Ds, and a potential difference alternates at the cyclotron frequency that accelerates the particle and increases the radius of its trajectory until it strikes the target. So basically, you have this magnetic field going back and forth that makes it possible to accelerate the particle until it reaches the right radius and hits the target. With if the speed that's desired is relativistic, then you can't have a uniform frequency. The frequency needs to be adjusted once the speeds become relativistic. And the reason is, if you go back to the equation for the cyclotron equation, if you remember from physics 2, it's equal to R equals mv divided by qb. In relativity, that becomes R is equal to gamma mv divided by qb. So so that product of m times v is the momentum, whether you're talking about and the momentum is not as simple as the mass times the velocity when the speeds become relativistic, at which point the cyclotron frequency f is no longer constant as v increases, that this becomes f is equal to qb over 2 pi gamma m. So suddenly it is dependent on the velocity as gamma becomes noticeably larger than 1. So synchrotrons, again, the magnetic field needs to be, sometimes you adjust the magnetic field instead of the frequency to account for relativistic speeds. Synchrotron radiation happens when the charged particles radiate energy as they accelerate. In a linear accelerator, the electrons are accelerated through alternating voltages. So the electron is accelerated through a positive voltage, through a positive potential difference. And then as it reaches the end of that potential difference, the voltage shifts. So now it's moving in the direction of increasing potential difference again. And so it shifts as the electron changes position to maintain the electron's acceleration. Now, also, you generate more energy if the target is not stationary, but rather moving in the opposite direction. So you want to create as energetic a collision as possible. And so sometimes the electrons are flying, or whatever particles you're talking about are flying around at super relativistic speeds. At that point, their energy, much like the energy of the photon, is simply equal to pc. Remember, the energy in relativity can be expressed as the square root of p squared c squared plus the rest mass squared times c to the fourth. Well, if the rest energy is tiny, is negligible compared to the kinetic energy, then you can simplify it by treating the energy as simply being equal to P times C. And so, by the 1930s, people realized that, that there were smaller particles than the protons, neutrons, and the electrons. And Hideki Yukawa predicted in 1935 that there would be a meson, a different particle, regulating the strong nuclear force. And Richard Feynman, an American scientist, developed the theory of quantum electrodynamics, which basically says that photons regulate the electromagnetic force. So there's, each force has a particle associated that regulates the force. So one example of a meson is the pi meson, and there are three types depending on the charge. So the pi plus meson has a charge of positive E. The pi minus meson has a charge of negative E. They're basically, the pi minus meson is the antiparticle of the pi plus meson. They have a rest energy of 139.6 mega electron volts. The pi zero, or the neutrally charged pi meson, has a rest mass of 135.0 mega electron volts. So it's not quite as energetic as the charged pions. So quantum chromodynamics, a theory that became associated with the Standard Model, which we'll talk about at the end of the chapter. The protons, neutrons, and other strongly interacting particles are made up of quarks. And so the strong nuclear force is regulated by particles called gluons. So, and gluons involve, gluons interact using, or act on quarks, is basically what that means. And so if you're talking about interactions with the strong nuclear force, you're talking about an exchange of gluons. With the weak nuclear force, the particles that regulate the weak force are the W plus, the W minus, and the Z0 particles. And so if there is a weak interaction, it involves one of those three, W plus, W minus, or Z0. And it's been hypothesized that there is a graviton regulating interactions involving the gravitational force, but gravitons have not been observed yet. So the positron is an electron with a positive charge and is considered the antiparticle to the electron. So the relativistic wave equation, Dirac expanded on the Schrodinger wave equation that we talked about earlier in the semester to include electrons moving at relativistic speeds. And it allowed for the possibility of antimatter. So basically, electrons moving not only allowed for the existence, it required the existence of positrons, which are basically electrons that also have positive charges. So the positron was first detected in 1932, but it would take until 1955 to observe the antiproton. So what you see with particle physics in general is that theory leads experimentation often by quite a sizable length of time. So a particle and its antiparticle will annihilate each other in a collision, producing gamma rays. So you put a positron and electron together, they will annihilate each other. All that mass will be entirely converted into energy. And so the same with the proton and an antiproton. So those are the highest energy um, uh, subatomic interactions that you can get. So the laws of conservation of energy, momentum, angular momentum, and charge are found to hold precisely in all interactions. And uh, and so when you talk about particle physics, it's important to keep track of the conservation laws. So nucleons have a baryon number of +1, and antinucleons have a baryon number of -1. So protons and neutrons have a baryon number of +1. Antiprotons and antineutrons have a baryon number of -1. And yes, it's possible to have an anti-neutron, even though even though it doesn't have charge. And so baryon number is also a conserved quantity in interactions. So leptons are any fundamental particles not made up of quarks. So basically, um, in particle physics, we talk about two types of fundamental particles, quarks and leptons. And so an electron is an example of a lepton. A muon is an example of electron. A muon also has a charge of -e. Again, E is 1.602 times 10 to the -19 coulombs. The mass is 106 mega electron volts. So the rest energy, 106 mega electron volts. So compare that to the electron, which has a rest energy of about half a mega electron volt. So it's quite a bit more massive. Electrons and muons emit different neutrinos, and so their neutrinos are also considered leptons. Electrons and electron neutrinos have an electron-lepton number of +1, while positrons and positron neutrinos have an electron-lepton number of -1. So muons also have a muon-lepton number, and their corresponding neutrinos do. And the antiparticles have a muon-lepton number of -1. These are also conserved in interactions. One of the uh, current questions in science is that electron neutrinos are reaching the Earth from the sun at a smaller rate than theory predicts. And it's also turns out that electron neutrinos can turn into muon neutrinos or tau lepton neutrinos. So this tau lepton is another type of lepton. And so the mass of the neutrino remains undetermined. Scientists are fairly confident that at this point that it is not zero. But they believe it to be about a millionth the mass of the electron. So smaller than we can really measure at this point. So the fundamental particles are believed to have no internal structures. Now, it's entirely possible that we'll create high energy collisions that can break quarks up into additional particles, or maybe even the electrons and the neutrinos. But that hasn't happened yet. And, there's no theory that calls for it either. So you have the fundamental particles, which again are the baryons and the quarks and the leptons. Composite particles are made up of quarks. So leptons exist by themselves, but composite particles are made up of quarks. And so we'll talk a lot about them. The gauge bosons are the particles that mediate interactions. So we've talked about that. Photons mediate electromagnetic interactions, which basically means if there's an electrical or magnetic force involved, there's an exchange of photons. If there's a strong nuclear force involved, there's an exchange of gluons. If there's a weak nuclear force involved, there's an exchange of W and Z particles. The leptons do not interact by the strong force, but by the weak force and by the electron force if they are charged. And so we've already talked about this. The electron and the muon, the tau particle is another lepton, and their respective neutrinos. So each of those leptons has a neutrino associated with it. Hadrons are composite particles or composite particles that do interact by the strong force. So the leptons interact by the weak force, hadrons interact by the strong force. Baryons are made up of three quarks, so protons and neutrons are types of baryons, and mesons are made up of a quark and an antiquark. So you have different types of hadrons, a baryon and a meson. And so you can see the different types that table gives the different properties, all of which are conservable and are conserved in interactions. You have the rest energy, so you can't have more energy put in than, or you can't end with more energy than you started with, and you can't have particles of less rest energy than the particles you initially had. So don't forget, energy is also conserved and charge is also conserved. So the lifetime of an unstable particle depends on which force is most active in causing the decay. The weak force is 10 to the negative 13 seconds or longer. The electromagnetic force is on the order of 10 to the negative 6 to 10 to the negative 19 seconds. Strong interactions are the most unstable. They're 10 to the negative 23 seconds. And it's possible that the lifetime of a particle could be so short that we can only infer that it existed, that we can't observe it directly. And those type of particles are called resonances, where the particle is so short-lived that you can't see it, but you can infer its presence from the byproducts. And the resonance has a width, or a delta T, corresponding to the uncertainty in its energy. One type of property that you sometimes see in quarks is called strangeness. So the K, lambda, and sigma particles are always produced in pairs, meaning if an interaction produces one of these particles, it always produces another of these particles. They also do not decay as quickly as other strongly interacting particles. This led to the introduction of a new quantum number called strangeness that's conserved in strong interactions, but not necessarily in weak interactions. So if you have a particle, if the byproducts of a reaction produce one kappa, lambda, or sigma particle with a positive strangeness, then they'll produce another kappa, lambda, or sigma particle of the opposite strangeness. Which brings us to quarks. The term comes from a James Joyce poem initially, but Murray Gell-Mann and George Zweig named them quarks in 1963. So basically, and again, this is an example of theory-leading experiment. Quarks weren't observed until the 1970s, but that the hadrons consist of fundamental entities called quarks. Remember, hadrons are baryons and mesons, and we think baryons, that's three quarks, mesons, two quarks, one quark and an antiquark. And so there are 6 types of quarks: up, down, strange, charm, bottom, and top. And strangeness, charm, bottomness, and topness are conserved in all strong interactions, but not necessarily in weak ones. So again, mesons are a quark and an antiquark. Baryons are three quarks. And so you see the different quarks and the different properties that are associated with them. So the up and down quark do not have additional properties associated, but the strange is -1, the charm is +1, the bottom is -1, and the top is +1. And the charges are of a fraction. So E 1.602 times 10 to the negative 19 coulombs is the charge of an electron, but quarks can have smaller charges than that. So the up quark has a charge of +2/3 E. The down quark has a charge of -1/3 E. And so it works like that. And so you have the quark compositions for several particles. And notice the diagrams include colors that quarks cannot include, or that particles cannot include two quarks of the same color. So you have red, blue, or green. So there are different types involved. And so the proton is two ups and a down. The neutron has two downs and an up. So then we have different types of heavier hadrons and heavier baryons. So each type of quark has its own flavor, but comes in three colors: red, green, or blue. So the flavor would be up, down, charm, strange, top, bottom. And the baryons have one quark of each color. The mesons consist of one color and an antiquark of the quark's anticolor. So mesons and baryons are quite different in a few different ways. The fermion obeys the exclusion principle and has half integer spin. Bosons do not obey the exclusion principle, and they have whole integer spin. And so the carriers of the forces, so the particles that regulate the forces, are all called bosons. So again, they're called gauge bosons in particular. And so it was gauge theory that unified the weak and electromagnetic interactions. And so the theory of color and the Queller force is called quantum chromodynamics. So that's about the strong nuclear force. And so quarks are always found in groups that combined have no color. So you have three different colors, then there's no color in particular. You have one color paired with an anticolor, you have no color in particular. And so basically that's what that means. So the standard model combines gauge theory with quantum chromodynamics. So you have a theory that combines the strong, the weak, and the electromagnetic forces. So the W and Z particles have mass, but they're slowed down in the presence of a Higgs field. Interactions between W and Z particles are governed by a particle called the Higgs boson, which was theorized by Higgs in 1964. It took nearly half a century to confirm its existence, but it was finally confirmed in 2012 at CERN. It has a rest mass of 125 giga electron volts. So you think a proton, you're thinking almost 1 giga electron volt. So it's quite a bit more massive, and that made it hard to find. And Feynman came up with a way of visualizing the interactions at the subatomic level. And so he gives the example of a neutron decaying into a proton. So a neutron is two downs and an up. The proton is two ups and a down. For one down to change into an up, it needs to emit a W minus gauge boson, so a W minus particle. That has a charge of -1. So the down quark charge goes from a negative 1/3 to positive 2/3. And so you get the proton with its charge of positive 1. So the W minus then decays into an electron and an electron neutrino. So there is energy emitted. And so this is how a beta decay works, basically. And one of the quarks inside a neutron changes from down to up, emitting, like I said, the W minus particle in the process, which then decays into an electron plus an electron neutrino. So, unified theories have been developed to try to explain not only what goes on, in these high energy interactions, but there's still some significant unanswered questions. Why do protons and electrons have exactly the same charge or the same magnitude charge? Why does matter dominate over antimatter? So some big unanswered questions. So the standard model at present is considered to be a low energy approximation to a more complete theory. That a lot of physicists expect to find holes in the standard model as they work at higher energies, much the same way that Einstein showed that Newtonian physics doesn't work when you get to a high enough velocity. So the grand unification theories typically start at what's called the unification scale, which is 10 to the negative 31 meters. So we're talking very, 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 very tiny mass or sizes, that you would get, in the tiniest fractions of a second after the Big Bang. So we're talking particle energies on the order of 10 to the 16 giga electron volts. So at this scale, there's no distinction between leptons and quarks or any of the different forces. And so that's what they mean by symmetry, that everything is the same, at a small enough scale, and that scale existed in the immediate aftermath of the Big Bang, talking very tiny fractions of a second. Some unification theories allow for proton decay, but a proton has never been observed decaying. And based on what we know about that, the minimum possible mean life of a proton is 10 to the 33 years. So a very, very long time, assuming it decays at all. So theories of everything unify all the forces, including gravity. Again, so you get to that small amount and you get symmetry. And, that symmetry at some level should include gravity as well, or at least that's what it's expected. Most of the theories of everything involve what are called string theories, where fundamental particles aren't really particles so much as they're more like vibrating strings with standing waves than they are like point objects. And so each fermion has a corresponding boson, with at least the same mass, but in supersymmetry. But today's accelerators cannot produce these particles. So on one hand, we have no way of knowing right now if supersymmetry is on the right track. But as you can see from this chapter, theory has led experiment by quite a bit in plenty of cases. So we will see is what it all ultimately boils down to. And that brings us to the last chapter in the book, which is on astrophysics and cosmology. So we go from the small picture to the big picture. And so astrophysics is the use of physics to study the heavens. So it's not simply, astronomy, but more specifically talking about, applying physics, and in particular the best physics, the the most advanced physics at this point, to the study of the heavens. Cosmology is the study of the universe. universe. So basically everything inside it. When we look into space, what do we see? And so that's what cosmology is about. And astrophysics is about the application of physics to this study. The guiding physical principle in cosmology is Einstein's theory of general relativity. So we're focusing on gravity. Although, if you're talking about the immediate aftermath of the Big Bang, you're the other forces come into play at that scale. The general unit of measurement for distances when you're looking in space is 1 light year. The light year is the distance that light travels, or electromagnetic waves travel in a vacuum over the course of 1 year, which is approximately 9.46 times 10 to the 15 meters. The Milky Way is a flat disk of stars extending to great distances in a plane. Well, it's not exactly a plane, but it can be approximated fairly well as a plane, much like our solar system can be approximated fairly well as a plane. Our solar system is not all that three-dimensional. So the Milky Way has a diameter of 100,000 light years and a thickness of only 2,000 light years. So obviously, 2,000 light years is not nothing. So it's thickness, but it's tiny compared to the diameter of the Milky Way. So, I mean, you can approximate the Milky Way as being two-dimensional fairly accurately. The mass of all the stars in the galaxy is estimated to be 3 times 10 to the 41 kilograms, about 11 or 10 to the 11 solar masses. Oftentimes, stars group together in clusters, that they appear from a distance to be a cloud. And other things you'll find in the galaxy are called nebulas, which actually are clouds of gas or dust. So about, maybe a century or two ago, the first people who made detailed looks at the Milky Way using, the telescopes, identified a number of things as nebulae. But some of them turned out to be star clusters when you look more closely, or in the case of the Andromeda Nebula, as a distant galaxy. So galaxies are large collections of stars. The shape can be spiral, elliptical, or regular. The Milky Way is an example of a spiral galaxy, as is the Andromeda Galaxy. Galaxies are organized into clusters and superclusters. So the distribution of galaxies in space is not uniform. The galaxies tend to be grouped in clusters or in bunches. So now we're going to quantify stellar evolution and figure out from that how to estimate distances to stars, how to estimate brightness of stars, and that sort of thing. So the intrinsic luminosity is the total power in watts radiated by the star. So if you can figure out, the apparent brightness, which isn't that hard to measure, is the power per unit area reaching the Earth. So the intrinsic luminosity is related to the apparent brightness by the equation B is equal to L over 4 pi d squared. So if you have a means of figuring out d, the distance we are from that star, then you can figure out the intrinsic luminosity. The intrinsic luminosity mostly depends on stellar mass. So if you can figure out the luminosity, you can figure out something about the mass of the star. So surface temperature can be determined by the blackbody spectrum or Wind's law. So a spectral analysis can tell you how hot the star is. And the temperature gives the power output per surface area, which is not the same as the total luminosity, but it makes it possible to estimate the size of the star. So if you can figure out the luminosity and you can figure out the temperature, then you can figure out you can get an estimate of the size of the star. So you can get an estimate of the mass, you can get an estimate of the size. Stars most likely form as gas clouds called protostars. So you have these clouds of gas, mostly hydrogen, and gravity causes them to contract. So they're dense enough that contraction happens. They start to squeeze in. And as the mass contracts, the particles gain kinetic energy. And if they contract enough, they'll gain enough kinetic energy so that fusion can happen. The star ignites, or a star is born, for lack of a better way of putting it. When you have that moment of ignition, at that point, the released energy stops the contraction. Um, and the sun is believed to have enough hydrogen fuel to live 10 billion years, and it's of which it's lived 5 billion. So it's about halfway through its cycle. More massive stars burn through their fuel faster. So when the helium starts to dominate over the hydrogen, after you have enough fusion taking place, the core will begin to contract, but the fusion will become more intense. And so what happens is the core contracts, but the outer shell expands and cools, and the star becomes a red giant. So if you look in the night sky and you see red stars, those are stars nearing the end of their um, lifespan, and so they become red giants. The helium will eventually fuse into carbon. So eventually, so the hydrogen fuses into helium, and then you start getting, the fusion into the heavier elements. So this is how the heavier elements happen from dying stars. And so when as the helium starts fusing, that'll heat up the core. And so you have nucleosynthesis at that point. You start making heavier and heavier atoms. But the sun will most likely become a white dwarf. So relatively light stars, 8 to 10 solar masses or less, shed their outer mass, but the core continues to contract until the electron stars overlap, until the electron clouds overlap. And at that point, the contraction stops. But if the stars are more massive than that, they can contract further. And so atoms heavier than iron require a substantial input of energy. So what happens is at high enough pressure, inverse beta decay starts. Beta decay is when a neutron becomes a proton and an electron. Here, the proton and electron fuse to make neutrons. So you wind up having a core made up entirely of neutrinos, or rather of neutrons. And, the neutrinos get released. But as the neutrons start forming, this cools the core, causing a rapid contraction. So the core at this point is made up mostly of neutrons and is called a neutron star, which eventually reaches the density of an atomic nucleus. So an atomic nucleus by itself is very, very dense. And in a supernova, the contraction of the neutron star is accompanied by the release of the outer shell of the star in a catastrophic explosion. So as the core contracts further, the outer shell gets completely pushed away from the star very rapidly. And so that's what a supernova is. So if the neutron star, if what's left, still has a mass greater than 2 or 3 solar masses, gravity will collapse it to the point where light can't even escape. And so this is called a black hole. Now, another type of stellar phenomenon is called a nova. And that's when a star in the sky becomes very bright, but for temporarily. And what probably happens is that a white dwarf pulls mass from the binary companion. So you have a binary star, and the white dwarf is pulling mass from the companion star and making it expand. And this can lead to what's called a type 1a supernova, and it's believed the type 1a supernova have luminosities that are nearly identical to each other. And so it's used sort of as a distance marker. And so it's believed that a type 1a supernova is a binary star, but the added mass collapses the star. So you have a nova, but as the white dwarf pulls in more mass, it starts to collapse. And if it reaches a critical amount of mass, it can go supernova from that. So how do you measure distance? Well, the way you measure distances to nearby stars is with parallax. So basically, the apparent motion of the star against the celestial background. And so um, Copernicus's theory of the Earth orbiting the sun was called into question because nobody could observe parallax with the naked eye. And they speculated, well, wouldn't there have to be parallax? And the answer, if the Earth is moving around the sun, and the answer is yes, but the objects were too far away to observe parallax with the unaided eye, but you can observe it with a telescope, certainly for nearby objects or relatively nearby objects. So small d is the distance from the Earth to the sun, and capital D is the distance from the sun to the star, and phi is the angular shift that the star makes, sort of the angle of parallax, the shift in the angle that the star makes, over the course of the year. Then you can write capital D is equal to small d divided by the tangent of phi. And so a parsec is the value of capital D when the angular shift is 1 arc second, which is 1/3600 of a degree. So a degree is broken into 60 minutes and or arc minutes, and an arc minute is broken into 60 arc seconds. So an angular shift of 1 second means 1/3600th of a degree. And so that distance corresponds to 3.26 light years. We don't really have the means of measuring using parallax beyond a 100 light year distance. So we need to use other methods to figure out the distance to other stars. So you can compare the apparent brightness of stars that seem to be very similar to each other. You can compare the brightness of main sequence stars. So again, how does it look compared to stars that it appears to be, that we can say certain things about, and then you can take the ratio of their apparent brightness to and figure out the distance from that. Other type of distance markers are the Cepheid variables, where these are variable stars where their intensity goes up and down and up and down, and usually it's in a periodic variation, and the luminosity varies with the period related to the average luminosity. So if you can find a Cepheid variable, you can figure out its period, and that relates to its luminosity, and that relates to its average luminosity, and from that you can figure out distance. And then the other thing are the type 1a supernovae, and usually the more distant you get, the more useful the type 1a supernovae are for distance measurements. So this brings us to general relativity. So this was Einstein's crowning achievement. So special relativity is the special case when there's no acceleration involved and the velocities are constant. General relativity means there is acceleration involved. And so Einstein's assumptions that went into the theory of general relativity are that all the laws of nature have the same form in accelerated and non-accelerated reference frames, and that a gravitational field is equivalent to an accelerated frame of reference. And so basically we observe gravity the same way we would observe it if we were accelerating, if we were in an accelerated reference frame like an elevator or something like that, that the properties of gravity are no different, than the properties of being in an accelerating object, at least from the perspective of an observer. And so the implications are that light bends around massive objects. That's the big implication. Einstein was able to correct a discrepancy in Mercury's orbit, that Mercury's orbit did not, was different than what you would have expected from Kepler's laws of planetary motion that work perfectly well for the other planets. But that discrepancy is ultimately a byproduct of its close proximity to the sun. The last aspect of Einstein's theory of general relativity to be verified experimentally were gravitational waves. These are interactions between very massive bodies that can produce a form of radiant energy the same way that electromagnetic waves do. And this was first observed in September 2015. So the theory was published in 1915. So it was exactly 1 century between when Einstein suggested that if we look for gravitational waves, we'd find them, and when we were able to find them. It took a full century. But we looked at two black holes colliding, and we were able to find gravitational waves emanating from that interaction. So Einstein's principle of equivalence states that no experiment can be performed that can distinguish between a uniform gravitational field and an equivalent uniform acceleration. So basically, a laser beam in an accelerating elevator will appear to be deflected from the perspective of an observer on the elevator. But an upwardly accelerating reference frame is equivalent to a downward gravitational field. And again, so the acceleration is, gravity is no different than, being under the influence of gravity is no different than observing motion in an accelerated frame of reference. So a gravitational field will deflect light. This was verified relatively quickly. It took place during a 1919 total solar eclipse. A scientist named Arthur Eddington brought a telescope to South Africa. He observed the background position of a couple of stars that were relatively close to the sun and obviously couldn't have been observed in daylight. But because of the eclipse, he was able to observe, and yes, their position was shifted relative to their normal, how they normally appear among the background stars. So if gravity curves the path of light, then gravity must also curve space. And the shortest distance between 2 points on a curved surface is not a straight line. So in general relativity, accelerated objects follow the shortest distance in curved space-time. The math Einstein developed for this is quite intimidating, but we're not going to go through that at this level of physics. But if you go to graduate school, you might see it. So the degree of curvature depends on the strength of the gravitational field and is strongest in the vicinity of the black holes. So we can define a term called the Schwarzschild radius, or the event horizon, which is the closest distance that an electromagnetic wave can be to a black hole and still escape its gravity. And so that distance is equal to 2 times the universal gravitational constant, capital G, times the mass located inside the Schwarzschild radius, divided by c squared. So how do we observe the universe? How do we measure distances? How do we measure velocities? Well, much like sound, light and electromagnetic radiation consists of waves. And any wave is subject to the Doppler effect, meaning its frequency or its wavelength will be shifted depending on how quickly it's moving. And so most galaxies that we can look at, and pretty much all the galaxies that aren't relative neighbors, the frequencies of spectral lines, particularly of hydrogen, are shifted to the red, or to greater wavelengths. And so what that means is, from the Doppler effect, that they're moving away from us. So you look at the equation, the observed wavelength equals the rest wavelength, multiplied by the square root of 1 plus v over c divided by 1 minus v over c. So if v is positive, if it's moving away from us, the wavelength is going to be larger. And so And so most galaxies, like I said, other than our relative neighbors like Andromeda, which is actually approaching us, um, most galaxies are moving away from us. And Hubble uh, def- um, developed an equation, which is a simple linear equation relating the velocity that galaxies are moving away from us to the distance they are away relating from us. And it's a simple linear equation where the proportionality constant h is called the Hubble constant, which is equal to 71 kilometers per second per megaparsec, or 22 kilometers per second per mega light year. So if we observe a galaxy to be moving away from us at 22 kilometers per second, or 2.2 times 10 to the 4 meters per second away from us based on its Doppler shift, then we can assume it's about 1 mega light year or a million light years away. So, obviously there aren't any large galaxies that close to us. Andromeda is 2 million light years. But you get to galaxies much farther away, and that equation still applies fairly well. So again, nearby galaxies have a more random distribution of velocities. Like I said, Andromeda is approaching us. But the Hubble relation holds very well in general, that you look at other clusters of galaxies, maybe the relative velocities are shifted a little bit, but that shift is small compared to the velocity with which the cluster as a whole is moving away from us. So we can define the redshift parameter, which is the shift in wavelength divided by the rest wavelength, or the lambda observed divided by lambda rest minus 1. At subrelativistic speeds, the redshift parameter is equal to v divided by c. The scale factor is a measure of the ratio of the universe's expansion between t equals 0 and today. And so that's equal to d plus, or t, or excuse me, z plus 1. And so that's the ratio of d, which is the size of the universe now, over d naught, which is the size of the universe at a time t in the past. So we can relate velocity to time and distance to time from that. And so the age of the universe can be estimated using the Hubble constant. And what it gives us is an age of the universe of 1.4 times 10 to the 10 years, approximately 14 billion years ago. And so what happened 14 billion years ago? And based on what we can observe, the universe appears to have been come into existence with a sudden abrupt expansion. And in the late 1940s, George Gamow predicted that you can observe traces of the Big Bang from background radiation in the cosmos coming from all directions. So in the early stages of the Big Bang, there'd be no atoms, and the photons would get absorbed and re-emitted due to the high density. But once the atoms started forming, once you started to get structure, some of the photons would not get absorbed, and they travel indefinitely in all directions. And they cool as the universe expanded. And so you'd get a background corresponding to a certain temperature, that'd be fairly cool. And in 1964, that background radiation was discovered by Arno Penzias and Robert Wilson, working at Bell Laboratories in New Jersey. They were working with a radio telescope, and they kept finding this noise in every direction that they pointed the telescope, and they figured out that it wasn't a problem with the instrument, that this was something that was there. And so the background radiation was nearly uniform in all directions. And so the radiation corresponds to a black body of temperature 2.75 or 725 Kelvin. So basically, what Gamow expected it to be. And in 1992, a satellite called the Cosmic Background Explorer, COBE, measured slight differences in temperature in the background radiation. And those differences in temperature are necessary because the universe is structured. If the difference in temperature was absolutely or if the temperature of the background radius was absolutely uniform, there would be no structure in the universe. So it was important to see that uh, there is rather subtle differences in the background radiation. So the time it takes for light to reach us from an event is called the look back time. And so when we look at a distant galaxy, we are not looking as it is now. We are looking as it was maybe millions or billions of years ago. And so the surface of last scattering is the farthest distance spreading out spherically from the Earth at which photons were emitted without being reabsorbed. And it appears to correspond to a value of Z of 1100. So how does the Big Bang look? The standard cosmological model starts with Planck time, so the first 10 to the negative 43 seconds. The four forces were unified, so there was symmetry. There was no difference between the forces or the particles that interacted with them at that scale. In the grand unified era, between 10 to the negative 43 seconds and 10 to the negative 35 seconds, gravity distinguished itself from the other three forces. In the Hadron era, first the strong force broke symmetry, began to distinguish itself from the weak force and the electromagnetic force. And so that made leptons and quarks possible. In the inflationary scenario, and we'll talk a little bit about inflation in a couple of minutes, the expansion of the universe, or the universe expanded by a factor of 10 to the 40 in 10 to the negative 35 seconds. So there was an extremely rapid expansion. At 10 to the negative 6 seconds, nucleons and antinucleons mostly stopped forming. So the antinucleons were completely annihilated, but enough nucleons were left over to create the matter of the universe. And again, one of the big unsolved questions is, why is there more matter than antimatter? Or why was there more matter than antimatter? Now there's a lot more matter than antimatter. So then we go to the lepton era. So by 10 to the negative 4 seconds, the last hadrons had disappeared. And after about 10 seconds, electrons and positrons were no longer being created, and the positrons became annihilated. And then you go to the radiation era. So the universe was dominated by photons and neutrinos. Nuclear fusion started, but only temporarily, and not for anything more complex than helium. This lasted 380,000 years. So everything up to the radiation era, you're talking tiny fractions of a second. But then the radiation era lasts 380,000 years. Then you get to the recombination epoch, where electrons started joining nuclei. And photons, so the electromagnetic force started pulling electrons into nuclei. Photons became decoupled from matter, so meaning that they were no longer getting relatively absorbed, and stars started forming after about 200 million years. Again, the original stars did not have any heavy elements, but it was through the death of stars that the heavy elements were created. And so stars started forming after 200 million years and galaxies after 1 billion years. And that brings us to the inflationary theory, which was first proposed by Alan Guth in 1981. So I'm old enough to remember when this happened. Lack of curvature in the universe and the near uniformity in the cosmic background, including why it isn't entirely uniform. And so it's explained a lot of missing pieces as far as what was going on with the Big Bang. And that brings us to the ultimate fate of the universe. Inflation suggests that the universe's curvature is close to zero, But as far as whether it's exactly zero or a little bit positive or a little bit negative, that's still unknown. And which brings us to what the ultimate fate of the universe is. If it's negative if the curvature is negative, the universe will expand indefinitely. If the curvature is zero, it'll expand at a steadily decreasing rate. So gravity will slow the expansion down, but never bring it to zero. In positive curvature, gravity does bring it down to zero, and then everything comes back on each other. So the critical density is in the universe is 10 to the negative 26 kilograms per cubic meter. So if the density of the universe is greater than that, you have positive curvature. If it's less than that, you have negative curvature. And if it's exactly the right value, you'll have zero curvature. However, normal baryonic matter only appears to account for 5% of the critical density, or 5% of the energy in a flat universe. So where's the missing mass, or where's the missing energy? So it's been speculated, given what's been observed as far as the motion of galaxies, that there is additional mass in there, and that mass is called dark matter. It doesn't appear to interact with any electromagnetic radiation, but it's inferred from the gravitational influence on the rotation of galaxies. And dark matter appears to account for 20% of the universe's energy. Which brings us to dark energy. And in 1998, an analysis of type 1a supernova at varying distances throughout the universe showed that the more distant supernova were dimmer than expected given their speeds, which suggests that the acceleration of the universe is increasing rather than decreasing. And the question is, why? So there appears to be some additional energy that we don't understand in the universe. And so this is called dark energy that would account for this result. And so dark energy appears to account for 75% of the universe's energy. So there are still a lot of interesting questions in physics. And but that's the end of chapter 44. And that's the end of the material that we're covering this semester. If you have any questions before the exams, please let me know via email. Otherwise, I will see you on Friday for the lab final and then next Monday for the lecture final. So I'll talk to you soon.